dotted in some momenta and so on forever. So it's a sum of these complicated terms which you find when you do your Feynman diagram calculations. So that's just an example of how these numerators look like. I will give some specific example later on. Okay, so what's the point of this representation of the amplitude? The point is, in this format, you can make this duality between color and kinematics manifest. So in particular, the amplitude has color factors, and the color factors live in a Lie algebra. And therefore, they satisfy specific relations. So they satisfy Jacobi relation, or Jacobi identities. Let's assume I only have a 4-point diagram, so I only have 2 vertices. So let me first write it down. Okay, so diagrammatically you can represent this by these graphs. So first a non-planar or twisted diagram, and then we have the T-channel diagram, and then we have an S-channel diagram. So this is A, B, internal guy is C, and then D, E. So it's all the same. A, B, C, D. So these are, of course, are the obvious relations that this FABC satisfies. And there's one more relation, of course, which is that there's an antisymmetry property. So you can draw this like this. So this is supposed to be just an ordinary 3-gluon vertex, but it's twisted the legs over. So this is FBAC, and this is of course equal to minus where I have untwisted the legs. So A, B, C. So this thing is equal to minus that. So these are the relations that the F satisfy, or the color factor satisfies. So in general, you can add more and more color factors. You have more and more complicated diagrams. So in general, if we call this diagram I, and we call this diagram J, and this diagram K, then we will have a diagrammatic identity which looks something like Ci is equal to Cj minus Ck. And this could involve many more FABCs. And okay, so that's obvious. Of course, it's a Lie algebra. It's a gauge theory. But the point is that in this representation, we have another quantity which looks very similar to the color factor, and this is the kinematic numerator. Let's write that. So what we're going to do is we're going to require that whenever there's such a 3-term identity of the color factors, we're going to require that there's a corresponding numerator identity. And similarly, whenever there's such antisymmetry, whenever Ci go to minus Ci, because you have twisted some legs, we're going to demand that Ni goes to minus Ni. So this is the antisymmetry. Yeah.
Diagrammatic representation of Jacobi's identity.
Yeah.
The first 2 terms, C shouldn't appear in the external vector because C is some.
That's right. Yeah. So it's summed over here. Yeah. And in general, you can. I mean, that's a good thing to do at tree level, even for kinematics.
So there's a
Yeah.
type of C should be E.
Oh, here. Oh, yeah, yeah. Okay, good.
And the other one.
Yeah, yeah, yeah. Thank you.
That's
I think I screwed up. It should be here. Alright, that's good. Comment. Okay, good. Thanks. Yeah, of course you should sum over all the internal indices. So what's the point of this? Well, first of all, what it shows is that if you can find such enumerators, then they behave as a Lie algebra. They behave the same way as the color factors, and we know the color factors behave the way they do because they're part of a Lie algebra. So if we can rewrite the Yang-Mills theory, for example, in this format, then we know that there's some additional structure in this theory, and for lack of a better name, we can call it kinematical Lie algebra. Now we don't know exactly what the corresponding group is, or we don't know what the structure constants are of this kinematical Lie algebra. All we know is that we can do these rewrites and it's consistent. And it has been proven that this is consistent at tree level. And at loop level, it's been shown in many different cases. And I'll show you some cases later on. In general, it's not proven though at loop level that you can always do this rewrite, so that it remains a conjecture. So one thing you might wonder about, what are the numerators? I mean, I indicated sort of what they look like, but there's no formula I can just use to write them down, because they're not even well defined. The numerators of some Feynman diagram and some gauge, and in particular we don't know what gauge that is, and even if we write down in one gauge, it could also be written down in some other gauge, because these numerators are not gauge invariant. The individual Feynman diagrams are not gauge invariant, so these quantities are not so well defined. So what you can think of what we're doing here is that we're taking some objects which have a lot of freedom in them, and we impose a constraint on this freedom, which is this Jacobi relation. Of course, what we might worry about is maybe we're just constraining something which is unphysical. Maybe this condition doesn't actually impose anything meaningful on the theory. It's just imposing some constraint on the garbage in the theory, the pure gauge degrees of freedom. However, it was shown, this was also shown in our paper, that if you assume that this is true, then you can derive new relations between gauge invariant quantities. So in particular, there's a certain set of tree-level amplitude relations you can write down. And you can convince yourself that, we'll do it here. You can convince yourself that it's sufficient to calculate all color-ordered amplitudes of this form. So you can put 3 legs at the first 3 sites, and let me just pick the canonical 3, and then you cycle through all the other permutations. I guess we should call it M. So all of the set of all of this amplitude completely span all possible 3 amplitudes that you can compute. So this basically means that you can fix the ordering of 3 legs, and then you have to consider all possible other orderings. And this is, of course, very reminiscent of what happens when you compute string amplitudes, that you have an SL2 symmetry that you can exploit to fix the location of 3 particles. However, before we work these relations out, so there's a specific a way to relate all other amplitudes into this basis. So before we worked that out, this was not known. But so this will give an n minus 3 factorial basis of Yang-Mills 3 amplitudes. So these relations were not known, but they were later on proven in string theory by a number of guys, and it was also later on proven in field theory. So assuming that this is a correct constraint to impose enumerators, you get a certain set of relations that take you down to a basis of this, and then that could be proven later on because this is a gauge invariant statement. So just to give you a flavor of what these relations are, I'm just going to show you the 4-point relation. So in particular, let's say you have an amplitude which is not in this form. So you have 1, 2, 4, 3. So obviously you don't have 1, 2, 3 as the first three legs. So then you can rewrite it, and in this case it's a very simple relation. It's just this one-term relation. So all you have to do is you have to multiply by S14 over S24. And if I didn't say what these guys are, these Mandelstam invariances are just, of course, it's 2 times the dot product, Ki dot Kj, the momentum. So you can see here, for example, that in this amplitude, the 1,4 channel is missing, but in this diagram, in this amplitude, the 1,4 channel is present. So clearly, you have to multiply by S14 to remove that channel. And similarly, in this amplitude, the 2,4 channel is missing, but it's here, so therefore you have to put it in. So that's a simple motivation why you need a factor. As you go to higher multiplicity, again, these relations become more and more complicated. And you can show that these relations need to exist, otherwise KLT will not work consistently. So if it was that these relations were broken, KLT would be broken. Okay, so that brings me back to gravity. How is this way of rewriting Yang-Mills related to gravity? Now I shouldn't have erased the formula I had there before, so I have to rewrite the formula again. So let me just write the gravity formula. I hope you have the gauge theory one in your notes. So again, it's going to be a sum of cubic diagrams. And again, we're going to have this integration measure. And I guess I didn't say what this S is before, but this is just a standard symmetry factor of Feynman diagrams. Same as in Feynman diagrams. And then, before we wrote the formula, I guess it went the other way around, so we wrote Ni, Ci, and then Di. So gravity, the gravity formula, is all we're going to do is we're going to replace this additional Toff factor by another numerator factor. Because, as I said before, the numerator factors and the color factors obey the same algebra, so it's very natural to substitute one for another. But I didn't write Ni squared. I could have written Ni squared, but let's account for the possibility that these two n's can be different. They could be the same, but they could be different. So let's put a tilde on one of them to denote that they're different. So in particular, it's very interesting to consider the case when they're different. And for example, if ni belongs to, for example, n equals 4 superdiagonals, let me not write, well, let me do it. Okay, I think I have space. And then ni triddle could be another theory, but let's consider the possibility. I think I'm going to run out of space, so sorry, I have to erase this. So, ni triddle. So it could be n equals 4 on this copy as well. So this is gauge theory. And what do you get then? Well, you get n equals 8 supergravity. If you can continue to pick this to be n equals 4 superdiagonals, but then you can reduce the supersymmetry on this side. So you can pick n equals 2, and this will give n equals 6 supergravity. And you can pick also n equals 1 here, but let me not write that out. Let me instead write n equals 0. So n equals 0 is just pure Yang-Mills theory, without fermions, without any matter. And this is going to give n equals 4 supergravity. So the number of, in this construction, the number of supersymmetries just add up. And you get the corresponding supergravity theory. And you can continue this all the way down. You can also start having n equals 0 on this side, and n equals 0 on this side. And then you get the theory here, which is an n equals 0 theory, n equals 0 gravity, but it will have axions and dilaton in the spectrum as well. And that's, of course, exactly what you expect from string theory, so this is no surprise. And you can see why you have to have this states here. It's because each n equals 2 theory, each n equals 0 theory has two states. It has the two states, the two helicity states of the gluon, helicity plus gluons and helicity minus gluons. So there's two states here, two states here. So you have to have 4 states on this side. So that's the 2 states in GR, and then additional 2 scalars. Now this table here is really nothing new. It works exactly the same way in KLT. But what's new is that we can do this in any loop order. So this is well, we claim to be able to do it any loop order. So this is not just at tree level, but at any loop order L. So if you wish, you can think of this as the correct generalization of KLT, or a generalization of KLT to loop order, to higher loop order, beyond tree level.
Sorry, so the NI factors, they were uniquely determined in Yang-Mills?
No, they're not uniquely determined.
So I choose different NI?
Yes, so that you can choose various different NIs, and the point is that no matter what choice you make, you better get the same gravitational amplitude. And that's very non-trivial. But it is guaranteed. It is guaranteed to work, if you think about it a little bit. So what happens is that you have exactly the same freedom in Yang-Mills theory. So you have the freedom of changing one of the n's. But what happens is that that change of the n will cancel out exactly because this other n satisfy a Jacobi relation, right? So there's going to be some garbage here inside one numerator, but that's going to cancel out because this other numerator satisfies a Jacobi relation. So that's the mechanism why, in the end, Yang-Mills theory amplitudes are going to be gauge invariant, or they're going to be independent of this garbage that you can otherwise have introduced. And it's the same mechanism in gravity. Now that doesn't prove, of course, that you get the same correct symmetries. That doesn't prove that you get the diffeomorphism symmetry, that you get the correct R symmetry, and so on. But it does show that, regardless of whether you put in one set of numerators, another set of numerators, as long as they satisfy the Jacobi relations, they give the right answer, or they give the same answer.
But if you change,
yeah.
But now you're changing both factors of n at the same time, right?
Yes. So you can change both of them at the same time, as long as they satisfy, as long as one of them still satisfy your Jacobi relation. So, but what you can also do is that you can change one a completely arbitrary way, which is consistent with gauge theory. as long as the other ones satisfy Jacobi relations, you're still fine. So there's a little bit of wiggling room in moving things around, but it's not complete freedom. Yeah, there are some constraints that you have to satisfy. Okay, but it's a good thing that you mentioned, that these enumerators are not unique, and this is also related to the fact of why I didn't write down these enumerators. Now, to be a little bit more concrete, let me write down some numerators, which are very easy. So in particular cases, there are numerators which are gauge invariant, and because they're gauge invariant, they're simple, and they do satisfy appropriate relations. But in order to do that, I actually need to change my setup a little bit. So before, my color factors were all in the adjoint, so they were products of FABCs. But let me change that a bit, because in general, of course, gauge series can have in any representation, right? So let me just consider a more general representation. And of course, the adjoint is a particular subcase. So So what if I have a theory which has more particles than just adjoint particles? It can have adjoint plus, say, fundamental, anti-fundamental particles. Then the color factors will have more general generators. So let me consider that case, because in that case I can actually write down some very simple numerators. So do it. Well, I think I can erase this. So consider the case that I have an amplitude with 4 quarks. So we're gonna use spin helicity notation, which I think I don't have time to explain, but I'm not going to use it very much. So we're going to denote the helicities of the particles. So these are all quarks. And we're going to have a specific helicity, so these are wild fermions. And these are going to also have a fundamental representation. So this is going to be fundamental, this is going to be anti-fundamental, this is going to be fundamental, and anti-fundamental. So in particular, this amplitude is going to look something like this. So there's going to be a generator, I, J, T, K, L. And then it's very simple to do the Feynman calculation in this case. And what you get if you use this contraction of wild fermions, you get this spinor bracket, and you get this spinor bracket, and then over the S channel. This is this diagram. And for those of you who don't know this notation, let me just give some simple. Well, so this is defined as some Levi-Civita contraction of beta of 2 spinors. This is IJ. And these are essentially the solution. These are basically the wave functions of fermions. So in particular, these are functions of momenta. So in particular, this is just a solution to the Dirac equation. And in particular, what happens is that in this notation, you can write something like this. And this is just Sij. So you can think of this spinner bracket as a square root of the Mandelstam invariant. But that's all I'm going to review this notation. So that's this diagram. Now we can write down another diagram, which is the T-channel diagram. And let me not write down the labels. The labels are going to be the same. You can just move the labels down here and here. But this is going to be equal to TIL, TAKJ, and then 1, 3, 2, 4 T. So you can, for example, you can as an exercise, you can go home and calculate this to contribute to this diagram, these two diagrams, and you will find these expressions. And so this is going to be my C1 N1 over D1, I guess, and this is going to be what I call C2 N2 over D2. So I only have two diagrams in this 4-point amplitude. So I'm going to call that diagram 1 and diagram 2. Now, this numerator is actually completely gauge invariant, and therefore they satisfy. It should satisfy some relation. And in fact, you can actually see already what the relation is going to be in this case. And in particular, the relation that we find here is that n. Well, actually, I should have used a different labeling. This is fine. Okay. So it's going to be n1 is equal to n2, and well, let me. Should I use a different labeling problem? Let me call this the S channel, and this is the T channel. So then I put it S, S, and S, T, T, T. So we're going to have it. So NS is equal to NT, and depending on how you define the U channel, it's going to be plus or minus, but let's put a minus sign. So essentially, we're looking for such a relation, but in this case, there is no U channel diagram. So you can just set this guy to be 0, and then if we believe that there's a Jacob relation, the identity that we should find is that NS is equal to NT. And indeed, you can see that this is the case. So here's a very simple example where two numerators are related through something which looks like a Jacobi relation. Any questions? Okay.
So C1 and C2.
Yeah.
Sorry, C2.
Yeah, good question. So you might wonder what happened to the relations between the color factors. And in particular, if you just take this is CT, I guess, and this is CS, you will note that these two color factors are not equal to each other. Of course, you have to think a little bit whether that there is some secret relation that relates these two, but in general, they're not. However, this three-term identity, there is a corresponding U-channel diagram. And the corresponding U-channel diagram, no, sorry, that's not right. There's no corresponding U-channel diagram yet. So this identity is not there. But it happens to be that this relation is still there, and the reason is that if I would have now placed these quarks in that joint instead, then I would have